Is there any problem which would not profit from a better understanding of uncertainties, optimum tools for decision-making, and higher computer power? Maybe there are some, but we think that it is obvious that most problems would dramatically benefit from a fundamental understanding of what human beings call problem solving, thereby performing and experiencing it as thinking. Different to many human science-based approaches, however, we intend to achieve a better understanding of the process of thought by theoretically and practically realizing what one could name the most fundamental Turing machine, or in more profane words, a universal computer. Motivated by recent requests and presentations, but also by the principal interest of mankind in an optimized healthcare, we here concentrate on medical examples with respect to the motivation of better computer solutions. This, however, does not restrict the number of possible applications to this field. The attentive observer will immediately make out a great variety of other possibilities for what we are going to present. Let us pick just two apparently simple examples. Implants have become an important aspect in modern medicine, especially in an aging society with the goal of a fulfilled and comfortable life, also for those who did their duty to society and now want to enjoy their final years in peace and harmony. It is inevitable to offer such solutions. However, even in the most modern and sophisticated medical environment, failure is omnipresent and by far too frequent to consider the current situation acceptable. This author has therefore spent a lot of his resources to develop suitable models and optimization tools for improved implant development. Unfortunately, however, the sheer number of structural possibilities and the complex nature of natural human tissue renders the task of finding and constructing optimum and truly satisfying solutions impossible. What we need is not only a better understanding of the materials, dynamic processes and interaction, but more computational power to allow for brute force calculation of multidimensional problems arising with this application. Another possible application could be seen in finding better treatment solutions for cancer. The current situation is far from good or satisfying. Even in cases where the patient can be healed, the suffering and the side effects caused by the state-of-the-art measures are too often unbearable. A perfectly side-effect-free and painless treatment is seen in the so-called monoclonal antibodies. Here, however, we have to adapt a complex organic system, namely the monoclonal antibody, to a single and always very individual counterpart. In other words, not only every patient is unique, but also its cancer. This renders the task of analyzing the cancer and patient genome and finding its perfect antibody solution a 10 to the power 24 faculty problem, at least, and requires all computers in the world put together to work for many years only for one patient with only one cancer problem. Similar complexity occurs in many other fields, like weather and climate simulations, anti-aging concepts, socio-economic prediction making, medicament and antibiotics development, financial market analysis, biosystem evaluations, and ecologic modeling, etc. Here something completely different would be of need. Richard Feynman once said that in order to calculate and understand a quantum object, one should build a quantum computer. Our reality, however, is a quantum gravity one, and thus, we say in order to completely understand it, we better build a quantum gravity computer. Understanding its fundamental theoretical principles and along the way laying open its core features shall be our starting point. But before we come to that, we should briefly elaborate how we came about to even consider such a quest. Briefly, after in spring 2018, the New Scientist had published an article about quantum computers apparently being even more powerful than suspected, we, which is to say my company, obtained a very funny request. It read like, "Dear Dr. Schwarzer, is there a chance to use your approach and evaluate a most fundamental Turing machine, one which also includes the quantum computer?" Our guess was that the sender had got wind about our recent publication and simply worked down a list of all possible candidates appearing, no matter even how remotely, potentially capable of answering his question. After tracing back the request to a company being involved in a project of Terminator developments, however, we lost our interest in the service order, but not in the task itself. So, what would be the most fundamental starting point for the construction of the most fundamental and universal computer? As humans tend to put their own desires and preferences into the things they intend to create, we here explicitly want to stay as general as possible and therefore simply take an arbitrary ensemble of properties, which want to exist in accordance with a minimum principle. This simply means that the ball always rolls into the valley, and would not like to be placed on the hilltop. The rest now is pure math, and the outcome, as surprising as it may be, are the Einstein field equations. Our field equations, however, act in an arbitrary number of dimensions and do not necessarily only describe space and time. Now the attentive observer will probably argue that there seems to be missing something. After all, everybody knows that the Einstein field equations are not compatible with the quantum theory, right? Is this so? Admittedly, usually Einstein's field equations are thought to deal with things like moving planets, galaxies, collapsing stars, and of course, black holes. So there doesn't seem to be much space for the quantum theory, which only shows itself with the very small things, like molecules, atoms, and elementary particles. But still we could try for some more or less unusual transformation we perform on solutions to the Einstein equations. Let this be motivated by the bold assumption that others simply might have overseen something. So in the first line of this slide, we have such an unusual transformation, and in the second line we have evaluated the so-called Ricci scalar. There is no need to know the exact meaning of the Ricci scalar, as it totally suffices to memorize that it has something to do with the curvature of space-time, and that it is just the most important ingredient or starting point for the evaluation of the Einstein equations in the first place. Closely observing our result and studying its intrinsic degrees of freedom suddenly gives us one of the most important quantum equations. It is called the Klein-Gordon equation, and it contains the better-known Schrödinger equation and the Dirac equation. As a mere byproduct, we contain the result that mass and the classical potential is just curvature of space and time. So, the quantum theory already resided inside Einstein's general theory of relativity. It was only hidden somewhere in those field equations. Can it really be that simple? We definitely have to look for a bit more proof. Let's just start with the most simple solution in 4 dimensions, where we try to find a scalar field, which we assume to be a constant. Now, and here I must ask you not to scream, suddenly we obtain the Higgs field. The very field some even named the God field, and which gives all particle its mass. Ah, yes, and talking about the devil, what is mass anyway? Well, with the new approach, we easily find the answer. Mass is the entanglement of 2 dimensions. The next quest should be to answer the question how and where black holes store information. The answer can be found purely mathematically and simply is: black holes store information bit by bit as dimensions. Thereby more dimensions means more information and vice versa. As a byproduct, we also find the internal structure of black holes and extract the information that they probably do not contain a singularity. Having gotten this far, we should ask, what is time? Sorry folks, you misunderstood. The question is not, what time is it, but what actually is time? As before with mass, we find the answer as entanglement of at least 2 dimensions. Thereby, we have a significant paradigm shift. Not time makes the process, but the process brings about time. It should be noted that we find a similar paradigm shift with respect to our notion of space, but here is not enough room to give a sufficiently deep elaboration and discussion. We therefore suggest to have a look at the references being given at the end of this video. So, as a kind of intermediate conclusion, we might say that after bringing general problems into metric form and quantizing them, we have a very general tool to attack every problem, and thus go from theoretical ideas to real applications. Some of these applications can immediately be realized and brought out to a hungry market, especially things like a universal uncertainty budget calculator for any kind of prediction making, or an IA-supported decision-making assistance are even planned as apps for a vast and still growing internet community. These products can be seen as immediate money spinners, but within this presentation we want to concentrate on something even more fundamental, if not to say fantastic. Of course, there are also immediately many philosophical questions and quite some consequences too, but the only thing we want to concentrate on here is the question about the most fundamental computer machine there could be within this universe. As most of our consideration is already published and would take quite a long and, what is more, rather boring time to elaborate, we shall leave it to the interested viewer to check our evaluations and directly move on to the currently most promising way for realization of the first quantum or even quantum gravity computer. Here we have the classical quantum dot deposition, the Australian silicon doping with phosphor on a variety of biocompatible solutions by the means of organic spin molecules. Here we only pick the quantum dot deposition, where indium arsenide is being molecular beam deposited on gallium arsenide. The size difference between the indium and the gallium then leads to a strain-driven self-organization, which bring about the desired quantum dot structures. Still, there is a long way to go before we could use these structures in properly working quantum computers, but at least there already is a start. But why all this fuss about the quantum computer? What is so special here? Well, while the classical computer can only handle zeros and ones, which is to say 2 different states, the quantum computer uses reals and does all possible states in just one circuit time. This gives an immense calculation power in comparison with the classical machine, at least for a variety of tasks. But having now also a metric approach for the understanding of the inner working of such a bit, we do not only see how the computer does achieve this all-in-one-moment calculus, but we also realize that such machines could be even more powerful. In fact, one might come to the conclusion that the intrinsic power of a single Einstein quantum bit could be the one of a whole universe, and it even could be a universe of its own. Some of you, especially in connection with recent suggestions for applying artificial enforcement to a human brain, will find this very disturbing, and we agree. But we also are of the opinion that reasonable use of artificial intelligence is always much better than natural stupidity. We already mentioned that there are immense products and product lines which could be brought to the market right now. However, we consider the total potential of the whole as being in the range of another Manhattan project, and perhaps even more. Thus, we are also looking for investors. At the end, we give a few related references for those who are interested in the mathematical background and more. Many thanks for your time and attention.